Hello, my name is Pascual Munoz. I am Associate Professor at the Technical University of Valencia. In this talk, I will review the fundamental concepts of sensors, using photonic integrated circuits. This is the general outline of my talk. In a first section, I will give a brief background information to put the audience into context. Then I will follow to terms and definitions commonly employed in photonic chip sensing. The last part of talk is a review of some of the currently employed chip sensing architectures. Finally, I will derive some summary conclusions. So let's start with the background section, where we will revisit the basic concepts of sensors, photonics and photonic integrated circuits. Very briefly, we will also review how sensing with photonic chips started, as it is known today. The closing part of this section is a fancy view of the application fields for this photonic chip sensing technologies. Let's start then with the concept of sensor. A sensor is a device that responds to a physical stimulus, and gives as a result a sort of impulse to be read out. There are several types of sensors. A list is provided in the slide. Just as a curiosity, the Monk hygrometer is a very rudimentary, yet smart working sensor. It was invented in the late 18th century. The Monk hygrometer indicates the type of weather one should expect: rainy, windy, humid, etc. And it is basically built with some sort of biotissue that contracts or expands with changes in ambient humidity. Photonics is the science of mastering light, from generation, through processing, switching, amplification and detection. And there are a huge number of applications. These applications are basically determined by the wavelength of light, ranging from visible up to the far infrared. Finally, this slide tells us what is a photonic integrated circuit, or photonic chip. It is a device where some optical and/or electronic devices are put in a substrate, that in most of the cases is a semiconductor material. The concept was formulated by Miller in 1969. You can see some photographs of photonic integrated circuits in the bottom part of the slide. They are typically just a few millimeters square. Let's go briefly to review the history of photonic chip sensors, as they are known today. To do so, I did a search on commonly employed citation databases. The results show that the 80s are the ages where some groups start reporting photonic chip sensors. One of the first is, again, a sensor that responds to changes in the ambient humidity. It is a corrugated light guiding structure, known as grating coupler, that allows to divert a beam of light in and out of the chip plane, at a given angle. The experimenters observed accidentally a change in the in- and outbound angle, that were due to changes in the humidity in the vicinity of this grating. Another photonic chip sensor, the Mach-Zehnder interferometer, was also proposed by those years, and we will describe it afterward. In the following set of slides, I provide a visual representation of the main application domains for photonic chip sensors. They are extensively used in the fields of bio, chemical and safety and security. In bio and life sciences, photonics is used to determine the presence of molecules, and/or to quantify number of them, or their concentration in solutions. For instance, they have been used as DNA, RNA, lipid, glucose and protein sensors. In the field of safety and security, these sensors have been applied to the early determination of the presence of hazardous gases, for instance as carbon dioxide. They have been also used to detect toxic gases, that appear for example during firefighting with halides. Finally, in analytical chemistry applications, further away than gas analysis, that are not detailed in the image since the granularity is very fine. Let's proceed to the next section, where some definitions of terms and figures of merit used in the photonic chip sensing literature are introduced. But let me first revisit what is an integrated optics waveguide. It is a sort of light conduit on a chip. Light may travel within this conduit by several means. One of the mostly employed mechanisms is total internal reflection, or abbreviated as TIR. In a TIR waveguide, the light bounces back and forth on the interfaces between the core and the cover of the waveguide. Some basic electromagnetism is needed, in order to find an accurate description of the ways light propagates within a waveguide. Those of you familiar with electromagnetism may surely know that there are several propagation ways, also called propagation modes. Depending on the orientation of these modes, one speaks about transverse electric, TE, or transverse magnetic, TM, fields. This is pretty important, having in mind a sensor application using an optical waveguide, as we will see in the next slide. To illustrate this fact, let me show the solutions for the propagation modes in a commonly employed silicon chip waveguide. The view graphs show the intensity of both the TE and TM propagation modes. As you clearly see, the TE intensity is contained within the core of the waveguide, whereas the TM mode intensity is somehow in touch with the surroundings. The part of the light that is actually not in the core, outside the center, is called evanescent field. Hence, sensing is possible when this evanescent field is in contact with other substances. These modes have a fundamental property that describes the propagation, which is called effective index. It is a sort of average among the refractive indexes of the materials from which the waveguide is built. It is also dependent on the wavelength of light, as well as on the waveguide dimensions. Hence, the effective index basically depends on the materials used for the core, the lower part, known as substrate, and the upper part, known as cover. Developing this a bit, the view graph shows a waveguide where the light travels from left to right, through a core of a given material, that has some refractive index in the core, on top of a substrate. For those of you that are not very familiar with the refractive index, let's just say it is a fundamental property of a given material. Hence, if a sample of certain material is put on top of the waveguide, part of the evanescent field will sense the effect of that material. And the material may either absorb, or just let light pass through, or both. This will ultimately change the propagation property of a mode, that is the effective index, mentioned in the previous slide. This is the concept of evanescent field sensing. Regarding evanescent field sensors, two types of sensing are usually differentiated. Homogeneous sensing, that is the case for which the substance to be sensed is distributed all over the cover. The substance to be sensed is commonly known as analyte. Hence, in homogeneous sensing, the analyte extends further away than the evanescent field of the optical waveguide. On the contrary, surface sensing is the case for which the dimensions of the analyte are small, compared to the extension of the evanescent field. In this next slide, the view graphs for TE and TM of a silicon waveguide are shown again. In fact, both can be employed for sensing. But, as a general remark, it is clear from the graphs that homogeneous sensing will usually rely on TM modes. This is due to the fact TM evanescent field is larger than TE for this silicon waveguide. Meanwhile, for surface sensing, the use of TE or TM modes for sensing is much more dependent on the dimension of the deposited analyte, as well as on the particular materials involved, both in the waveguide and the analyte. Just on this additional view graph on the same slide, we see the effective index change, for a change in the refractive index of both an homogeneously analyte, or a surface deposited analyte, and for different materials as well. With this set of slides, we have introduced the concept and mechanisms of evanescent field sensing. Let's continue with typical metrics that are employed to quantify the effects of the analytes. The first metric is termed refractive index units, abbreviated as RIU. It is defined as the amount of change in the refractive index of the analyte, or cover. As mentioned before, a change in the refractive index in the cover influences the propagation mode property known as effective index. So how much RIU gives certain effective index change is usually employed as a measure of sensitivity. For example, in the lower left graph we see a sort of sensor, a Mach-Zehnder interferometer, we will describe in detail later on. The readout of such a sensor is named phase change, and it is induced by a refractive index change in some part of the device. The Mach-Zehnder response follows a cosine law. Very briefly, a phase change of 2 pi is the maximum argument drift of a cosine function, to prevent uncertainty. Hence, one can correlate how much RIU are required to give this 2 pi drift. The next metric is known as mass density, that can be sometimes expressed as a concentration in a solution as well. It does actually refer to the accumulation of mass on the sensor surface. I won't go into the details here, but when it comes to comparative concentrations, it is usually better to use molarity units, rather than percentages. This is due to the fact different molecules do not have the same weight, and some experiments are rather more dependent on the number of molecules, than on actual weight. The last metric I wish to introduce is the limit of detection, or abbreviated LOD. It is the smallest amount of analyte that produces a quantifiable, or measurable, output. And it can certainly be specified using units of both of the previous metrics. In any case, it is very important to note that LOD is very dependent on the instruments, as well as on the conditions employed to extract the measurable quantity out of the photonic chip. For example, in the previous case of the Mach Zender, one might achieve better LOD in terms of RIU with a better, for instance less noisy, measurement setup. Yet the sensor chip would be exactly the same. LOD is typically used to compare the performance of sensors. Given the previous advice on molarity, note it is not actually fair to compare LOD of different sensors using molar units, unless the molecules of all the experiments have the same molecular weight. That is the reason why usually RIU, or mass density, are employed. The view graph on the bottom right side of the slide has both molarity and mass density in the y-axis scales. But, reading carefully the figure caption in the source paper, the conversion between axes is done assuming the same molecular weight for all the different experiments. In this slide, I show an example of LOD extracted from the cited reference. The paper uses a given sensor architecture, the ring resonator, that we will also review in the next section. The sensor is used to determine the concentration of IL-2 antibody in a solution. The transduction evanescent field effect, in these rings, is achieved by means of a tunable laser. A tunable laser has the ability of changing the emission wavelength. In short, for those not familiar with tunable lasers, it changes color of the emitted light by some amount called tuning step. Therefore, LOD in this case is basically determined by this tuning step. In the view graph, this is marked by a red horizontal arrow, labeled with the words 1 picometer. Hence, going down to the x-axis, which represents the antibody concentration, 1 picometer tuning step corresponds to a concentration of 1 nanogram per milliliter. In conclusion, LOD is determined here by the step of laser, but the sensor is still a refractive index sensor. Note that, for a practical use, this sensor requires some calibration, that is, some previous process where the concentration is known by other means, for instance regular chemical analysis, to build the transduction graph shown in the slide. Finally, just 3 slides to close this section, where some concepts, related to parts not directly on the chip sensors, are presented. Firstly, the concept of labeled versus label-free sensors. A labeled sensor makes use of a marker that is attached to the target molecule to be sensed. Hence, the presence of the molecule is determined indirectly by the presence of the marker, rather than directly by the presence of the molecule itself. On the contrary, a label-free sensor will directly monitor the presence of the target molecule. Secondly, let's briefly introduce the concept of transduction. We saw in the previous slides how the presence of an analyte can change the fundamental propagation property of light in a waveguide, known as effective index. But, how is this effective index change translated into a measurable quantity? This process of transforming the change of effective index into the change of other magnitude is known as transduction. In the particular case of biosensors, the latter can be one out of this 3-phase amplitude or frequency change in the light propagating through the sensor device. Transduction is usually achieved by the combination of an evanescent field waveguide with other relatively more complex waveguiding structure. Hence, the overall sensor chip will yield a magnitude change, phase, amplitude or frequency, for the probing light outgoing the sensor. Thirdly, let us review what is functionalization. It is the process of preparing your sensor to host the analyte, in order to ensure interaction between the substance and the evanescent field of the sensing waveguide. The graph shows an example on which a silicon nanowire, that is chemically modified to include molecule receptors. The target molecule will bind to these receptors, placed in the vicinity of the waveguide core to cover interface, that is, where the evanescent field is strong. With all these concepts, let's move on to complete the picture of on-chip photonic sensing, with the architectures, that is the layouts, that allow to traduce the evanescent field sensed changes to a measurable quantity. Let me tell that not all the possible architectures are reviewed here, and refer you to the references within the slides, for further information. So to start, let's talk about the silicon wire. A silicon wire is a strip of silicon on a silica substrate that, as already described, has a large TM evanescent field. And this wire can indeed be embedded as part of more complex photonic circuits, as Mach zenters, and rings, as we will see later. But, the fact is the wire is a very fundamental block, because of the evanescent field. Nonetheless, some other structures exhibit comparatively larger evanescent field, as the slot waveguide, described in the following. The slot waveguide is actually composed of two silicon wires, which are separated by a very small gap. This is depicted in the top graphs, in 2 and 3 dimensions. What it is impressive is that, most of the light is actually guided in the tiny gap in between the wires, as shown in the bottom left graph. But, despite having a larger evanescent field, one common issue is how to properly fill the tiny gap, usually some tens of nanometers, with the analyte. Another waveguide-based sensor is the bimodal waveguide. This is actually an straight waveguide, that supports more than 2 sensing modes. Just to explain it in comparison with the silicon wire, it would be as having 2 TM modes, with different propagation conditions, that is, with different effective indexes. The interaction of each mode with the analyte changes the effective index differently. Therefore, at the end of the sensor, the combination of the 2 modes, also called interference, depends on the interaction with the analyte. A widespread interferometer for photonic chip sensors is the Mach zenter. It is a photonic device where light is diverted in 2 different paths, and later on combined again. If the paths are ideally identical, all the light is combined into the output. A difference in the paths results into less light combined in the output, compared to the ideal case. Hence, a sensor can be built, for example as shown in the top graphs, with one of the arms opened, to sense the analyte. As mentioned earlier, the light intensity at the output follows a cosine law, which is directly related to the phase change induced through the evanescent field in the sensing arm. There are indeed more advanced versions of this, like the 2x3 outputs Mach zenter interferometer shown in this picture. A less commonly employed interferometer is the Young interferometer. As in the Mach zenter, the light is separated into different paths, and each one can be in principle functionalized with different receptors, whereas one of the arms can be kept as reference. The transduction scheme, instead of a plain light intensity readout, as in the previous case, is the pattern of the light going out the Young sensor. This pattern is recorded with a CCD camera. The pattern changes, depending on the composition and amount of analyte that is sensed, through the evanescent field, in the arms of the Young interferometer. The last of the interferometers is less common, and it is a proprietary technology by its inventor, Hartmann. The sensing principle is the same then for the Young interferometer, a set of sensing and reference waveguides. The interference is created between them by means of on-chip optics, that can divert and combine beams from the different waveguides. This gives an intensity change similar to the Mach zenter interferometer, that is read in a photodetector array. And to close this section, let's present the ring resonator. It is a circular waveguide, coupled to a regular straight, or bus, waveguide. It is a particular type of the, so-called, microcavities, where the light revolves several times, and it does combine with the light coming from the bus. This creates an interference pattern, which usually exhibits a dip in the spectrum. To be precise, certain wavelengths, or colors, are suppressed. The particular color suppressed, and/or the amount of suppression, It is dependent on the refractive index of the annulete on top of the ring. The annulete is sensed through the ring resonator evanescent field. The transduction for ring resonators is usually some sort of spectrometer, either a broadband light source and a tunable filter, or a tunable laser and a photodetector. So, in conclusion, we have reviewed the fundamentals of sensing using photonic chips. These sensors leverage on the unique features of photonic chips, such as stability, miniaturization and production scalability. They find applications in a wide number of domains, but the most important are life sciences and analytical chemistry. We have reviewed some of the concepts that describe the on-chip interaction of light and the annulete. Finally, some of the most commonly used chip architectures, that is circuits, employed to transduce the effect, induced by the annulete, into a measurable quantity, have been shown as well. That is all. Thank you, and do not hesitate to forward your questions through my Twitter account and/or by email.